We're back, and this little section is really just a small piece of Verilog and some of the design flow. There's a site that it's taken from, and it's a very good site. It's got lots of nice examples, and it's used here and there throughout the course. Initially, everything you know is done from a schematic. More recently, evolution is toward a hardware description language such as Verilog, and it has the associated code development cycles associated with it. The example we're going to look at is a 2-bit arbiter. Specifications are 2 bits, active high with asynchronous reset, fixed priority, agent 0 having priority over 1, and grant will be asserted as long as the request is asserted. Here's the high-level block diagram of it. It allows you to determine what your inputs and outputs are going to be a little bit more easily, and that would correspond to the module in Verilog. Here's the inner workings of that module. It's a finite state machine. Circles are the states, and the arrows are the state transitions. So here's the code and the interface for the arbiter, module arbiter, and it has a clock, a reset, request signals and grants signals, and then the declaration of whether they're inputs or outputs. A variety of data types in Verilog. A wire would be used for connecting 2 points, register data used for storing values, and there's others as well as scalars and vectors. Some of the operators, they're like C counterparts, often taking 2 values and compare them, otherwise operate them to yield a third result. First example, A is equal to not B, or A is equal to sum of B plus C. The control structure is a very C-like: if, else, repeat, while, for, and case, as you'd expect. Begin and end act like the curly braces in C or C++. So here's just an example where it is, the widths and bits, the base and the number are represented differently down here for this little bit of code. Here's an always block, and it always fires at A, B, or select being sensitive, or changing because it's sensitive to these, and then it'll run this bit of code. So y will equal 0 if select equals 0, y will equal A, else y will equal B. So it's a 2-to-1 multiplexer, and it's a combination logic block when it's synthesized. You can also use functions, and again, functions save you the trouble of rewriting things. You can use them when you need them, and basically makes the common routines that you're going to use over and over again a little bit more convenient. Back to the arbiter here. Okay, this is what we saw before. The only difference here is the grant 0 and grant 1 outputs are registered, and in this particular case, always at a positive edge of the clock or a positive edge of reset, we do the following. If the reset, set the grant 0 and grant 1 to 0. If request 1 is 0, then or request 0 is 1, then you set grant 0 equal to 1. Else if request 1 is equal to 1, then you set grant 1 equal to 1. So you should be able to simulate that. In addition to that, that code up there should be synthesizable. The traditional mode would use a simulator such as Model Sim, which you have access to through Altera. You drive the inputs, you set them to what you want them to be, watch what the inputs are, and see that they're as what you'd expect. More recently, people spend a lot more time writing test benches, and basically it's code for exercising your design. So it makes your life a lot easier. Here's where the code would go for the arbiter, and then this test bench code. So it's another module. It's an arbiter test bench. It has the clock, reset, rec 0, rec 1, has wire signals, grant 0, grant 1, and it has an initialization and a begin. So in this case, you're saying I want to monitor request 0, request 1, grant 0, grant 1, request 0, request 1, grant 0, and grant 1. So these are just the one-to-one correspondence in terms of what you want to represent them as. So initially you have a setup of clock 0, reset 0, request 0, and request 1 equal to 0. At 5 nanoseconds or picoseconds, whatever the time is, the reset goes to 1. At 15 more, the reset goes to 0. 10 more after that, request 0 goes to 1. 10 more after that, request 0 goes to 1. So you can see you can build up whatever pattern of inputs you want, and it finished off basically telling the simulator to finish with the $finish. So here's where the clock is set up. So at 5 unit intervals, clock goes to not clock, and then the interface for the device under test. So it's a U0 instantiated with the .clock being clock, the .reset, the request 0, request 1, grant 0, and grant 1, and then the end of the module. So it brings us to assignment number 0. using model sim, simulate that arbiter. This should be synthesizable in hardware. And if you have any ambition, you could fix the arbiter, because what you'll find out in this particular case, if you implemented that code, it really only goes between the two states of the grant and grant being granted. The grant request being granted. The second part of the assignment is using model sim to simulate the arbiter with the test bench. And this part here probably is not going to be synthesizable to hardware, and you wouldn't be able to synthesize it if you tried to. Your output should look something like this. This is running with the test bench. These are all the signals that were run, and these are the ones from the arbiter from the test bench, the U0 interface. So you should be able to get something like that. This brings us to the end of Chapter 1. You should have a basic understanding of how ICs have evolved, as well as their design environment or environments. Certainly be aware that you have a very super high density CMOS. Perhaps that'll become a lot more obvious in the next little while. Obviously, lots of CAD support for building these circuits, and some of the technology you should be getting familiar with, like the terminology, the ASIC for application-specific integrated circuit, the FPGA, HDL for hardware description language, the SoC, system on chip. Perhaps a little less familiar terms like standard cell. In any event, you should certainly have an appreciation for the complexity involved in building an integrated circuit, largely derived by virtue of the fact that the devices are so small and you have so many of them to work with. So that brings us to the end of